I'm sharing the screen again. So this will be a quick review of functions. This you must have already studied in the past, and it will be a refreshing review for you. I'll be sharing these notes with you. All right. Just on calculus, on single variable, I have a compilation of 28-page notes, which is not very detailed, but it is also not too short. It is right for you to grasp and review all the basic concepts that you have learned in the past. Okay, so let's begin. So, a basic definition of functions. What is a function? What is domain range? So let A and B be two non-empty sets, and F is a relation which associates each element of set A with unique element of set B. Then it is called as a function from A to B. So let us consider two sets, set A, set B. In very simple terms, you have some elements here, say X or X1, X1, X2, X3. And set B has say Y1, Y2, Y3. All right. Now, what is the definition of a function? That it's a relation. There are so many types of relations you can make. We'll not go into details. We are just focusing only on what is a function. One such relation is a function. When every element of A is involved in the mapping, all right, like X1 is mapped to Y1, X2 is mapped to Y2, and X3 is mapped to Y2, let us say. Now, and so first part is if F is a relation which associates each element of set A. This is the first part. Every element in set A must be included in the mapping. Second, it is associated with a unique element in set B. That means X1 is mapped only to one element. It cannot happen that you have, X1, X2, X3, Y1, Y2, Y3. You cannot have that X1 is mapping to two elements in set B. If this happens, then it is not a function. Okay, this particular relationship is not a function. Okay, this is a function. All right. So there's a basic that we learned. Now this, and also suppose X3 is not involved. Again, it will cease to be a function. So X1, X2, X3, all are involved. So this particular set of A with these elements is called as the domain, and the set B is called as the codomain. This we know. So we write as function that maps set A to set B. All right. Then so A, so now for example here we write here f of x1 is equal to y1, which means that x1 is associated to y1 under this functional relationship. Okay, f of x1 is equal to y1. So this y1 is called as the image. It is called as the image of x1 under f. And x1 is called as the pre-image of y1 under f. All right. So here I have given this example and I'm showing here, but here it is said like that. If A belongs to set A is associated with B belonging to set B, then B is called the image of A under F and is denoted as f of A equal to B, and A is called as the pre-image or inverse image of B as denoted as f inverse of B is equal to A, such that f of A is equal to B. All right. Now, an element of B can have more than one pre-images. Achha, very important part. These concepts can come in your general aptitude. It may not directly come in your engineering maths, combined with permutation combination. So when we come to that, I will give some examples and show how these concepts will come. So look here. This y2 is an element in B. What are its pre-images? X2 and X3. These are the pre-images of y2. So elements in B can have more than one pre-images. Okay, but elements in A cannot have more than one images. That is the important part. Next, what is range? Range is set of all the images. Set of all the images is called as the range. So here in this particular function, we see that the codomain has y1, y2, y3, but the number of elements, the elements that are occurring as images are only y1 and y2. So the range of f is y1 comma y2. So the domain A is x1 comma x2 comma x3. The codomain B is y1 comma y2 comma y3, but range is y1 comma y2. All right, and we denote range like this. F of A is f of x for all such that x belongs to A. So all the values of function, all the values of f of x put together gives you the range. Okay, this is a basic that we have learned. Now there is a representation of functions. How do you represent functions? And there are different types of functional representations. So in set form, the functions are represented as set of ordered pairs like this. 1, 2, 2, 4, 3, 1, 4, 3 in the example that we have taken here. All right, we can write the function as f is equal to, in this example, what will be f? It will be x1 comma y1 comma x2 comma y2 comma x3 comma y2. This is the function as the set of ordered pairs. All right, now this is easy as long as it is a discrete, your domain and range are discrete for discrete sets. This is a valid representation. But for continuous sets, that means your domain is a continuous set of real numbers. Like your domain is 0 to 10, set of all real numbers between 0 and 10. Now you cannot keep writing how many numbers are there between 0 and 10. Infinite number of real numbers, and it is impossible to represent using this set form. So that is why there is an algebraic relation form. So we write function as, an expression, an algebraic expression. Y is your value within the codomain, is a function of x, and it has certain expression. Here we have taken x plus 1. This is an expression, and all the while we deal with functions with these expressions. So the functions can be, most of the times we deal with functional expressions like this. I'm just said algebraic relation. It need not be an algebraic relation. It can be trigonometric, logarithmic, exponential. So all the transcendental functions that which are not algebraic, they have a functional representation. And each of the function, both set of ordered pairs as well as algebraic, they can be represented on a graph. So very important to understand, because graphical understanding is extremely important in calculus. So let's do that. Just a second. So what is a graphical representation of a function? On the horizontal axis or the x-axis, we plot the domain. All right, and on y we plot the codomain. All right, now we had x1, x2, x3, y1, y2, y3, discrete. Okay, the discrete graph. Now when you plot the graph, x1 is related to y1. So this particular point represent your functional relationship f. Then x2 relates to y2, and x3 in our example also relates to y2. So this is a representation of the function. This is a function. Of course, it's a function which is breaking. It is not a continuous curve. Now let us plot this function now. Y is equal to x plus 1. Right? We know what it is. It is a straight line. Just a second. Yeah, it's a straight line. So this is the graph. So it is a continuous set of infinite points which lie on this particular line. this is your functional expression. So function is expressed also as a graph. So at any point, say, so at x equal to 2, the value of y is 3. So now at 1.5, it will be 2.5. And at 2.99, the function value will be 3.99. So it is set of all values of x comma y which satisfy this particular equation. So this is a graphical representation of a function. So now I'll not go into more details. This is just I'm just introducing or reviewing the concept and going forward. Wherever it is important for you for gate, I will stop and explain further. Okay. Now this we will just go through quickly, but at the same time it is important. Remember, we deal with in integral calculus, we deal with areas and volumes of figures. All right. And for that, having a grip of understanding of functions is very, very important. So that is why we need to know some types of functions. So they are one functions, and they are many one functions, and they are onto functions. This is the classification of the mappings. So one, many one, onto, and into function. So let us look into that. There's one more classification. Yeah. This is important for us. So let's go back to this example. I'll copy the same example. So this particular representation of a function, I'll call it f. So there's a function f mapping a to b. Now this is not one function. Why? Because two elements in a is mapped to or associated with one element in b. So this cannot be called as a one function. So one function or injective mapping is if no two elements in A have the same image in B. So here, no two elements in A have same image in B. So one. These things will become very important in finding areas. All right. Now the fundamental understanding of it. So whereas the same thing I take, now I change the mapping. Now look at this. I change the mapping now. So let's say x1 maps to y3, x2 maps to y2, x3 maps to y1. Now this is a one mapping. Why? Because different elements in A have different images in B. No two elements in A have the same image in B. All right. There are questions in permutation combination which come in your general aptitude of find the number of functions that are possible. Set A is given to you, set B is given to you. number of one functions that are possible. All right, these things will come up. So that time we should be knowing what is a one function, so that we don't make a mistake. So that's why I'm going through this. These other points you can, I'll just highlight it. Methods to check one. For a one mapping, usually when you draw a graph for a one function, so let's say just now we drew a graph of a straight line. So again, we draw a graph of a straight line. All right. And also we will draw a graph of a circle. Circle is itself not a function, so I will not draw a circle. Just a second. Yeah, let's say I draw a parabola. Okay, this is like y equal to x square, and this may be y is equal to x minus 1 or so. Okay. So now let us consider these two graphs. If I draw a horizontal line, I draw a horizontal line. Now what happens when this horizontal line cuts the curve at only one point? Here you see, it cuts the curve only at one point for this particular line. So this is a one function. This graph represents a one function. It is not just one horizontal line. You draw any horizontal line throughout the graph from negative y-axis to positive y-axis. It will cut the curve only at one point. Whereas for a many to one function, this cuts at 2 points or more points, many to one function. Now, this is very useful for us in integral calculus, because if there is a symmetry, we can do integration of half and then half the function, and very easily we can do. So we have to know the symmetry part, what is 1 1, what is not 1 1. So a function, so this is not 1 1, it is many to one. A function which is not 1 1 is called as many to one function. Clear? Next is onto or into. Very simple. Again, onto function means onto function means that every element in B is an image of at least one element in A. So every element in B is mapped. So this particular here y3 is left over. So this is not a onto but an into function. Whereas here y1, y2 and y3 all are mapped. So this is an onto function. This is an onto function. So for an onto function, the range is equal to the codomain. The range is equal to the codomain. That is an onto function. Next, so we have done 1 1, many one, onto, into. Then there is bijective mapping. Bijective mapping is that which is 1, 1 and onto both. So this example here that we are seeing here, this is both 1, 1 and onto. So this is a bijective mapping. This is 1, 1 and onto. Okay. Now I'll test your knowledge of functions, all these things, basics, and soon when we draw graphs. So graphically, it is very, very essential to understand how 1, 1 onto. And then again, very important, when you come to calculus, differential calculus, you can understand by calculus how the function is 1, 1. If the derivative of the function is always greater than or equal to 0 throughout the domain, and this, then it is an increasing function. That means the function will be 1, 1, or it should be either the derivative should be throughout positive or throughout negative. Then it's a 1, 1 function. For example, what is derivative represent? If we remember our basic calculus, derivative represents slope of a tangent at a point, isn't it? So now let us look two examples here. Y equal to x cube, y is equal to x square. Okay, both these examples we will have a close look. Okay, y equal to x cube. I'll change the graph a bit. Okay, this is y equal to x cube, and let's do this, y equal to x square. Okay. Now here, look at the slope of the tangent. At any place you take a tangent, it will have a positive slope. Okay, draw a tangent, it has a positive slope. Anywhere you draw, it has a positive slope. That means the inclination of the tangent with the x-axis is acute. All right, anywhere you choose, it has a positive slope. So throughout it is positive, except at x equal to 0, it is 0. So this is satisfied. F dash x is greater than or equal to 0, the slope. And this particular function you can see is a 1, 1 function. It's a 1, 1 function. You can draw any line which is horizontal. It will cut the graph at only one point. So this is a 1, 1 function. Whereas you see here, you draw a line parallel to the x-axis, it cuts at 2 points. It is many to one function. Okay, why many to one? You have two values of x connecting to one value of y. That's why it is a many one function. Understand? Two values of x, whatever this value is, 1.75 or something, or you take -2 and 2 here, -2 and 2 both map to 4. So two values of x, -1, -2 and 2 are leading to one value of y, that is 4. So that is why it is many to one function. Now what happens in many to one function is, you see your slope now, slope of the graph, slope of the tangent. At this point, the tangent is having a negative slope. At this point, the tangent is having a positive slope. Tangent is having positive slope here. Tangent is having negative slope here. So what we can observe is, throughout your f dash x is not having the same sign. It is negative and then turning to positive. Therefore, it will not be a 1-1 function. Okay. This is the graphical understanding of 1-1 functions. So okay, domains and ranges, I will leave it to you to review. I'll not go into detail of it. I'll just discuss the basics of basic functions and their standard domains and ranges. I will not dwell into it because this is not so critical for us from GATE point of view, but you can go through it. Go through the basic definitions I've given here. Something that is very important for us is even and odd functions. Even, odd, and periodicity. This will be used so much in calculus. Of course, it is not, domains and ranges are the basic in calculus, but I choose to do it along with the when I do graphs of functions. That is when I'll do that for you. Now, even odd functions, again, I'll explain graphically. A function is said to be odd if f of minus x is equal to minus of f of x. And a function f of x is said to be an even function if f of minus x is equal to f of x for all x. Okay. So tell me, what is this function, even or odd? Please participate.
Odd function, sir.
Yes, it is an odd function. Very good. What is this function?
Even functions.
Yes, this is an even function. So this is an odd function, this is an even function. So the reason is f of minus x will give us minus x cube here, which is minus of f of x. And f of minus x here gives us f of x only. Now the graphs of this odd and even functions, we can see here we have already plotted. This is odd and even function. The graph of an odd function here, I'll copy it here for completion. Okay, I think I'll explain it here only. So the graph of an odd function will be odd symmetric about the origin. That means if one part of the graph lies in one quadrant, the other part will lie in the opposite quadrant. So here it is first, when x is greater than 0, the graph lies in the first quadrant, and the same reflection lies in the second quadrant. So how do you get this reflection? It is like, take any point on the curve, make it to pass through the origin, a line, and when it cuts the curve at the other point, this other point will be the odd symmetric image. Let's say this point is P1, this point is P2. The midpoint of these 2 points will be the origin. So it is odd symmetric. So for example, you take a, all right, let us take x equal to 1 for argument's sake. for x equal to 1, the value is 1. But for x equal to minus 1, the value is minus 1. Okay, here. So 1 comma 1 is a point on the graph. So minus 1 comma minus 1 will also be the point on the graph. Similarly, this is for an odd function. So odd function is understood by its symmetry with a negative sign about the origin. All right. So the points will lie in a symmetric way in the opposite quadrants. Whereas for even functions, the graph will be such that the graph will be symmetric about the y-axis. The graph will be symmetric about the y-axis. That is how an odd even function looks. And important, any function can be written as a sum of even and odd function. Okay, any you see here by this particular expression, f of x is equal to f of x plus f of minus x plus f of x minus of f of minus x upon 2. Now this part is an even part, this part is an odd part. You can check, you call this as g of x and h of x. So g of x is f of x plus f of minus x by 2. So you replace x by minus x, you get the same expression, f of minus x plus f of x by 2. And let's say h of x is this, f of x minus f of minus x by 2. You replace x by minus x, we get f of minus x minus of f of plus x. It becomes negative of h of x. So this is the even part and this is the odd part. So you can always get a function to be written as a sum of odd and even components. This is what happens in the Fourier series expansions. All right, there we will see that. And then derivative of an odd function is even, and derivative of an even function is odd. Very simple, 3x x square, the derivative is 2x, which is odd. X square is even. So, and x cube derivative will be 3x square, which is even. Original function is odd. Okay, so this is sufficient for us. These are required for us in dealing with integral calculus. And of course, differential calculus and finding maxima minima, this also plays a critical role. So this pretty much the first class is that about functions. Tomorrow's class will be on limits. So, but I'll try to give you a brief of this. Now, what's a periodic function? Well, this has tremendous utility. This has tremendous utility, and we deal with periodic functions, very common, sin x, cos x, tan x. Okay, be it waveforms. Waveforms are filled with sin x and cos x. And whenever you have to deal with vibration or waveforms, it is a must that we deal with periodic functions. So periodic function is a function that repeats itself. The graph repeats itself. So if there exists a positive real number such that f of x plus t is f of x for all x belongs to R, then a function is said to be periodic. So now when t is the least positive value, then if t is the least positive value, it is called as the fundamental period. And if a function is periodic for period t, then it will be periodic for 2t, 3t, 4t. So we know some of the periodic functions. All right, what are they? Trigonometric functions are periodic. All right. Okay. So trigonometric functions are periodic. Sin x, cos x, I'll take tan x. See, here, let's expand it further. Graph repeats itself, and we know a period of sin x is 2 pi. We know it. So at every interval of 2 pi, the values repeat. This interval 2 pi, the values repeat here. Here, the values are repeating. So sin x is a periodic graph, and for tan x, at every interval of pi, the values repeat. The function value repeats for every interval of pi. So 0 pi. So these graphs we need to be quite thorough with. So periodic functions, this is, and periodicity we can find out. Of course, for gate, they'll not go into find the periodicity and so on of a function, but you will have to intrinsically use it. All right, you just go through the notes that I've given here. Then most often we deal with composite functions. That is a function within a function. Composite function, I explain it in a very simple manner, that it is a function within a function. So here is an example of h of x is g of f of x. So f is a function of x and g is a function over f of x. So there's a function within a function. We call it g circle f and other things, but this is a composite function. So composite functions, and we deal with so many composite functions. Like example, let's say your h of x is log of sin x. It's a composite function. Or h of x is sine of uh, 2x, sine of, just a second, yeah, sorry, sine of 2x square plus 5x plus 1. Now, this expression itself is a function and sine is acting over it. So pretty much we keep dealing with these type of composite functions in our calculus. So here you see x maps to f of x, and then f of x maps to g of f of x. So here you have three, A, B, C, three sets. So x relates to f of x and f of x in turn relates to g of x. So directly x can be related to g of f of x. So that is a composite function, that's all. So of course the domains and ranges. So for this function to exist, x has to be within the domain of the function sin x, and sin x also should be, values of sin x should also be within the domain of log x. So those domains have to be satisfied. All right. So G circle F exists if range of F is a subset of domain of G. So for composition, an F circle G exists if range of G is subset of the domain of F. All right. Now, again, I'm not going into the domains, calculation, the domains. I'm just giving this. Now, properties of composite functions with odd and even. This is again useful for us when we do integral calculus. If both the functions are even, the composite will be even. If both the functions are odd, composite will be odd. But if one is odd and one is even, the composite will be even. Composite will be even. That means 3 of the 4 cases is even. That means either the inner function or outer function, if it is even, the function will be even. Okay, so that's the idea. So this is the basics of functions, and we know what are inverse functions. If f maps A to B, f inverse maps B to A. That is the inverse. So A to B is a 1-1 function, an onto function. Then there exists a unique function G mapping B to A. So let us do this. Of course, for inverse to exist, function should be bijective. It is a 1-1 and onto function. So in our example that we had looked into, we'll go back. You had x1, x2, x3, y1, y2, y3. x1 had mapped to y3, x2 to y2, and x3 to y1. All right, this was f mapping A to B. Now f inverse will be the reverse. y1 will map to y3, x3, y2 will map to x2, and y3 will map to x1. So this will be a inverse mapping. F inverse maps B to A. Okay, just the inverse mapping. Now, interesting things to note is, yeah, of course, your domain of F will be the range of F inverse, and the range of F will be the domain of F inverse. All right, and the functions will be symmetric. F and F inverse, the graphs of F and F inverse will be symmetric about the line y equal to x. Why so? We can always see that. I will show this. I'll not be able to show it in this. Let me try. Let me try. Y is equal to x cube. Y is equal to cube root of x. Yes, I'll be able to show. Okay. So cube root of x is nothing but an inverse of x cube. And we can observe that if you draw this line y equal to x, all right, the graphs will be exactly symmetrical. This is cube root of x and this is x cube. So graphs will be symmetrical. So inverse functions will be symmetric about y equal to x. There's again a useful trick for us in calculating of areas under curves. So this is, I just covered today. What I covered, I didn't cover anything new. I just covered whatever is the basics of functions, which you all, which we all should remember. We cannot forget when we are going ahead. We may be learning calculus, but these are the fundamental basis of functions. Now, I'll share with you an important handout. Just a second. Yeah. Okay. So I'll be sharing this handout to you of different types of functions. We will discuss this. One important is logarithmic functions. This, of course, logarithms is part of your syllabus for general aptitude. Okay, but it is very much integrated within calculus. So we will have to learn that. So I will discuss logarithms now, but I'll be giving this handout to you in which we have, I have given all the basic trigonometric formulae and basic, all basic trigonometry and inverse trigonometric functions. All properties are given in that, and logarithms is given in that. In addition, I'll be giving this one to you. Okay, all the basic functions, their domain, range, and for all the standard functions, what is the domain, what is the range. So right now I'll go one by one with this, with the graph, and also let you know exponential, logarithmic, algebraic, so on. So first we'll discuss these are not types of functions, these are types of functions for classifications. These are different types of functions: trigonometric, logarithmic, and so on. So here we need to know the graphs of this function, which will help us later in differential calculus and integral calculus. Okay, the first type, algebraic functions. One of the most simple ones, this is the identity function, y equal to, or f of x is equal to x. This is the identity function. All right. So we know what the graph is. It's a line passing through the origin. We know it. I want you all to participate now. Make your unmute your microphones. I want you all to participate. So there's the graph of y equal to f of x. Now tell me these things. What is the domain of this function? What is the range of this function? Whether it is even or odd? Is it periodic? Okay, and is it invertible? Okay, 1 1 onto bijective. What is its property? Okay, now please share. Please participate freely. Yeah, tell me, what is the domain of this function? It's review only. What is the domain of this function?
Minus infinity to plus infinity.
Minus infinity to infinity. So this is all set of all real numbers. Okay. Or we write open minus infinity to infinity. What is the range? Range is set of all the values of y that this function takes. If x is taking all infinite values, y will
Range.
also take?
All real numbers.
Yes, all real numbers. Good. Very good. Then is it an odd function or an even function?
Odd function.
Very good. Very good. It's an odd function. Why? F of minus x is equal to minus x. Minus f of x. Other way, if you see the graph, you can see that the graph is symmetric about the origin. So this is an odd function. Is it periodic?
Non-periodic.
Yes. So it is non-periodic. What about its nature? 1 1 onto into?
One.
Yes, it is 1 1 for sure.
Onto also.
Yes. So it is 1 1 and onto 1 1 because every value of x has a different value of y. There are no two values of x which will give you same value of y. That we can see that graphically, you draw any line, any horizontal line, it will cut the curve only at one point. So this is a 1 1 function. This is a 1 1 function. Y equal to x is a 1 1 function. All right. It is 1 1 and onto. So it is a bijective. It is invertible. F inverse exists and F inverse is again equal to x. F inverse, the inverse function is the same as the original function because it's the identity function. So similarly, let us do for this y equal to x square. This is a function f of x equal to x square. Yeah, please tell me. All the same things again. Domain, range. So tell me the nature of this function. What's the graph? What will be the graph of this? Before I plot it?
U-shaped.
Mm.
U-shaped between positive.
It is a parabola.
Yeah.
All the graphs of whichever are quadratic will be parabolic. This is a parabolic graph. Any graph of the form is y equal to ax square plus bx plus c. This will be parabola. Now, if a is positive, the parabola opens upwards. If a is negative, parabola opens downwards. So that's only. So it's a parabolic curve. Now, what is the domain? Domain is set of all values for which the function is defined. So what is the domain?
Minus infinity to infinity.
Yes, correct. Good. So domain is R. What is the range?
0 to infinity.
Good. 0 included or not?
Included.
Very good. Very good. 0 is included. So sometimes students write it as R plus, which is wrong. If you just write R plus, it excludes 0. So it is 0 to infinity. Is it even or odd?
Even.
Even. Very good. Very good. Is it periodic?
Non-periodic.
Non-periodic. Is it 1 1 onto invertible? Please tell. Others also participate.
Neither 1 1 nor onto.
Okay, it is neither 1 1 nor onto. Very good. So it is not 1 1, it is not onto. So therefore it is not bijective. This is correct. This is correct. All right. So of course, if you define, suppose you define this f, okay, suppose you write y is f of x equal to x square such that f maps 0 to infinity to 0 to infinity. Then what happens? Then we are restricting our graph only to the positive axis. All right. Only in the first quadrant. Function is defined. So the second, the negative side doesn't exist. All right. In this particular case, this part doesn't exist. So we only have this graph. This will be 1 1 and onto. Understand? This will be 1 1 and onto. Why? Because the domain, the entire domain is mapped, and this is the codomain 0 to infinity. The entire codomain is mapped. So range is equal to codomain. So it is onto. It is 1 1 because you draw a straight line parallel to x-axis. It cuts the curve only at one point because this left side doesn't exist. Understand? So the functions which are not 1 1 and onto, they can be invertible provided you make a restriction in the domain. That is what happens with inverse trigonometric functions. All right. So of course, I'll not repeat y equal to x cube. It will be similar to y equal to x, all the patterns. It will be same. X square and all. Now let us go to the important function. Let us go along with this exponential, and then we'll go to logarithm. So first we will take this y equal to a power x. Now a should not be equal to 0 and a not equal to 1. And comma, a has to be positive. A cannot be negative. So we can write this simply as two conditions, that a not equal to 1 and a is positive. So that includes a not equal to 0. All right. Why these two conditions? Very, very important. If a equal to 1, you just get a straight line like this. Now this curve we just cannot handle, meaning we don't know what to do. It is neither 1 1 or it's just a constant function, no matter what x is, if a equal to 1. So you don't get any useful thing from it. Okay. So how is the plot of this curve? Oh, it is plotted for a equal to 1. I'll change it. Are you able to see the graph? Are you able to see the graph on the right side?
Yes.
Yes.
So when a equal to 1, it's a straight line. For a as number between 0 and 1, you will get a curve like this. And for negatives, it will not exist on. Okay, for positives, it will exist. I'll expand it so that we can see. Yeah, this is good enough. Now, this is equal to 1. When a is greater than 1, this is the curve. Real numbers behave very peculiarly. So, when a is greater than 1 and the power of x goes higher and higher, you know, a power x goes higher and higher. So, I'll put a equal to 2. Let us see. Yeah, insert on this page. So, this is a equal to 2. All right, this is the graph. Now I'll put a is equal to 0.5, that is 1 by 2. All right. So this is a equal to 0.5. So generally when a is greater than 1, this will be the graph. When a is less than 1 but greater than 0, this will be the graph. Okay, it will keep changing, of course, but this is a typical graph. This is for a equal to 2, this is a equal to 1 by 2. So as x increases, so a is 2, right? So 2 power 1 is 2, 2 power 2 is 4 here, 2 power 3 will be 8, 2 power 4 will be 16, 2 power 5 will be 32. So the graph exponentially keeps increasing. And when you go to negative side, x is negative. This is very, very important in limits. It is very important in finding areas under curves. And this graph is very, very important. Limits. So you see when x takes smaller and smaller values, x equal to -5. If x equal to -5, you get 2 power -5, which is 1 by 32. All right. And when x is equal to -10, it is 1 by 2 power 10. And so on. As x keeps decreasing, the value of this value almost goes to 0, but never equal to 0. A power x will never be equal to 0. All right. When a is a fraction, it is the opposite. When x is negative, the function value will go to infinity. And when x is positive, the function value approaches 0. Okay. Now you tell me, what is the domain of this function? What is the range of this function? Is it even or odd? Is it even or odd? Is it periodic? That's what we. And is it invertible? Yeah, please start. What is the domain?
Minus infinity to infinity.
Very good. Very good. Domain is R. Minus infinity to infinity. Range?
Zero to infinity, sir.
Very good. 0 included?
No.
No.
Very good. Very good. Excellent. 0 to infinity. So here we can write range as R plus. Okay. 0 is not included. Is it even or odd?
Even.
Even.
Is it?
Even.
No, it is neither even nor odd. It is neither even nor odd. Because for even function, it should be symmetric about the y-axis. It should be mirror images about the y-axis. Interestingly, these two you put together, they are mirror images of each other. Okay. This 2 power x and 1 by 2 power x, they are images of each other, but this itself is not a symmetric graph, symmetric about the y-axis. Okay, there is no symmetry. It is not a mirror image. You can see here. So f of minus x, you can see if you want to check even or odd, for say f of x is a power x, or let's say 2 power x, you take f of minus x is 2 power minus x, which is 1 by 2 power x. It is not equal to f of x. It is not equal to minus f of x. So it is neither even nor odd. Periodicity,
Non-periodic.
non-periodic. 1 1 on 2 into 1 1 on 2 into
1 1.
yes, it is 1 1. Good.
Not onto.
It is not onto. Good. But suppose I'm defined like this: f maps R to R plus. Okay. Domain is R. Codomain is R plus. Now tell me, what is the nature of this function?
Now it's onto.
Hmm?
Now it's onto.
Yes, good. Now it will be onto. It is both 1 1 and onto if this is our definition of the function. All right. So a power x is this. Good. Log function. Log function is the inverse of this function. Log function is inverse of a power x. Okay, y is equal to, again, let us study the graphs. It will be interesting. Yeah. So now again, you see when here important conditions that a should be positive and a cannot be equal to 1. If a equal to 1, see, it is defined like this. If a power y is equal to x, then y is log x to the base a. So why this, see, when you raise a number to a power y, then you get a value x. So we say the reverse is log of x to the base a is this y. So this exponent is log of x, the right hand side, to the base a. Okay. So this inverse. So naturally, when a power y is defined for a greater than 0 and a not equal to 1, so accordingly, the same conditions will apply. So here, now if you're observing the graph, you don't see the graph at all. All right, you're not able to see the graph at all. Now, let us change the values. I will take the same values, a equal to 2 and a equal to 1 by 2. Let us see what happens. So a equal to 2, this is the graph. So this is the graph for a equal to 2, a greater than 0. Now let us change a equal to 0.5. This is the graph. Yeah, a equal to 2 and a equal to 0.5. So here all log functions for a greater than 1 will be like this, and a lying between 0 and 1 will be like this. Okay, now tell me the domain range. I'll deal with log functions in detail when we do general aptitude. Those fundamental logarithm type problems I'll do there. Okay, but I will not go into that depth now. We'll just go more from calculus point of view. So tell me the domain, range, even or odd, then periodicity, then whether it is 1 1 on 2 into. So I will say F maps. Okay, first you tell me the domain, then only I'll write this. What is the domain? Yes, please answer.
0 to infinity.
Domain, very good. 0 to infinity, 0 included or no?
Not in.
Not included. Very good, very good. 0 is not included. Very good. So 0 is not included, because understand, the domain of log will be the range of exponential function. The range of exponential function was r plus. So domain of log will be r plus. It cannot be 0. 0 cannot be included. Now what is the range of log function? Range of log function. Look at the graph.
So minus infinity to infinity.
Very good. So range is r. Because as x keeps increasing, the log value also keeps increasing. Of course, at a smaller rate. X is 2 power 100 and a is 2 here. Okay, this we are dealing with a power. X is 2 power 100 and a is 2. So log of 2 power 100 to the base 2 will be 100. All right. X is 2 power 10,000. Log of x to the base 2 will be 10,000. Understand? So although it increases, the rate at which it increases will reduce, but it will keep going to infinity. There is no end to it, because x can take infinite values. Correspondingly, log x to the base a will take infinite values. So range goes from minus infinity to infinity. Very good. Next, whether it is even or odd. Is it even or odd?
Neither.
Neither. Very good. Very good. Then is it periodic?
No.
Not period.
Not periodic. Is it 1 1 or on 2? Now how should we define such that it becomes 1 1 and on 2? How should we define f? F maps
R plus to R plus. R plus to R.
r plus to r. Very good. If f maps r plus to r, then this becomes both 1 1. It is already 1 1. There's no question of that. It is just onto. Checking whether it's onto. So both of these are images, they are inverses of each other, a power x and log x to the base a. And there are properties of logarithms. Right now it is not so critical for us. The properties of logarithms you should I have given here. So with the graph, these are basics, you should just go through them. All right, and keep it. I will share this sheet with you. Okay. Now next in the list, exponential is over. Okay, this is modulus function is important, and then we'll go to step function and then trigonometric functions. Modulus function, a very important function. Or absolute value function. Okay. Now, before we draw the graph, how is an absolute value function defined? Absolute value of x. How is it defined? Anybody? Absolute value of x.
For x greater than or equal to 0, we'll take it as x. For x less than 0, we'll take it as minus x.
Very good. Very good. We are absolute value is the value without the sign. So when the this variable is positive, it is greater than 0 or equal to 0, it is equal to the variable itself. All right, but if it is negative, then it is minus x. All right, so now let us plot the graph, and then it will be easier for us to mark domain, range, and so on. All right. All right. So this is the graph. Now you please tell me all these factors. What is its domain? What is its range? Is it odd or even? Is it periodic? And is it, 1, 1 on 2 into so on? What is the domain? Anyone? What's the domain?
Minus infinity to infinity.
Yes. Domain is minus infinity to infinity. Set of all real numbers. Now, many students are silent. They should participate. Only 3 or 4 are participating. Others also participate. If you participate, you will get involved in it. What is the range?
0 to infinity.
Very good. 0 to infinity. Good. 0 is included. Next. Is it even or odd?
Even.
Very good. It is an even function. Okay, it is an even function. So you can see from the graph, it is symmetric about this line, the y-axis, x equal to 0. It is symmetric about this line. Okay, so graph is symmetric about the y-axis. So it is an even function, and you can show that f of minus x is modulus of minus x. Now, if x is positive, if x is positive, if x is greater than 0, this will be a negative value. So for negative value, minus of the value inside. So it will be x. And if x is negative, this will be the positive value, minus x will be positive value, it will be as it is. So you see, this function is x when x is greater than or equal to 0, minus x when x is less than 0. It is same as the original function. Okay. Another much more simpler logic is it's a modulus function. I am worried about the absolute value. Absolute value of minus x or absolute value of x, both will drop out the negative sign. So both will be equal. So therefore, f of minus x will be equal to f of x. F of minus x will be equal to f of x. So it is a even function. Now, is it periodic?
Non-periodic.
No,
It is
sir.
non-periodic. Okay, good. Is it invertible? Is it invertible? What do you say about 1, 1 on 2? Yes,
Not one, one, one.
it is
Not one, one.
not 1, 1. Very good. Very good. On 2? Why is it not 1, 1? Because you can draw a line, horizontal line. There are two values of x which will give you the same value of y. So it is not 1, 1. Is it onto? No, it is not onto if f maps R to R. Then it is not onto. Of course, if you define f in such a way that it maps R to 0 to infinity, then it will become onto. All right. Okay. Under root function, it's all right. Domain range. This is step function. Okay, I'll conclude with step function. And then as a homework, I want you to go through, I will send this straight away in WhatsApp group for today. For those of you who are not registered, that part I'll discuss right after the class. I don't want to discuss right now. I'm not in the flow of the class. I'll just discuss the step function. Of course, we don't deal with step functions so often in general mathematics, engineering mathematics, but in signals and systems, you deal a lot of step. This is also called as the greatest integer function. So we call this as the floor of x. Sorry, see, just a second. Yeah, greatest integer function. How is it defined? See, on a number line. This is a number line. So step x is the greatest integer less than or equal to x. Less than or equal to x. So if you have 0.75 as the number. X is 0.75. The greatest integer less than 0.75 is 0. All right. That is the greatest integer. So 0.75 will give the, the integral part. This is the integral part function. So let us say you have 1.5. What is the greatest integer function of 1.5 give? 1. All right. 2.99 something. 2.99. What will be the greatest integer function? It will give you 2, the value 2. This is interesting. Minus 1.25. Okay, this is the value, minus 1.25. What is the greatest integer step of minus 1.25? It will not be minus 1. It will be minus 2. Greatest integer less than or equal to that number. Okay. Similarly, this is minus 2.9, let us say. The greatest integer will be minus 3. Okay. This is the greatest integer function. And no matter what the values are in between, all will map to this function. So let us plot this. It is taking it as X. I'll have to do something. Okay, I'll plot it with hand. I'll plot this graph with hand. Now these are so 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4, minus 5. Here it is 0. So for any number that lies between 0 and 1, the value of the step will be 0. So value of the step will be 0. If it is equal to 1, it will be 1. The greatest integer. Now 1 can be written as 1 plus 0. So step value is the integral part. All right. So it will be 1. Now if it is 1.5, it is 1 plus 0.5. Step value is 1. So throughout here, you will get step value like this. Then between 2 and 3, this will be the step. Between 3 and 4, this will be the step function. Between 4 and 5, this is 1, 2, 3. Between 4 and 5, it will be again 4. Now coming to when it lies between minus 1 and 0, say minus 0.25, then the step will be minus 1. Okay. And at minus 1, it is minus 1. Then between minus 2 and minus 1, you get this. Between minus 3 and minus 2, you get minus 3 and so on. So this looks like a step. That's why it is called a step function, or the greatest integer function, or the integral part function. Now just tell me the domain for this function, range for this function, even odd nature of this function. periodicity, invertible. What is the domain? Quickly, please answer.
Minus infinity to infinity.
Minus
Yes. So it is R. What is the range?
Integer numbers.
Yes. It is only taking integer values. Between 0 and 1, it is taking 0. Then between 1 and 2, it is taking 1, 2, 3. So range is only the integer values. So it is Z. Set of all the integers. Z. Then even odd.
Odd.
Hmm,
Neither.
very good. It is a trick. It is neither. It appears odd because it is in the opposite opposite quadrants, but only when it is integers, integer points, f of minus x is equal to minus f of x. Otherwise it is not. Otherwise it is not. You can see that. So let's say f of step of 1.5 gives us 1. Step of minus 1.5 doesn't give us minus 1. It gives us minus 2. So step of minus 1.5 is not equal to minus of step of 1.5. Clear? So it is neither even nor odd, and it is not periodic also. It is not periodic. It is not periodic because integer values are keeping on increasing. The function value is keeping on increasing. It is not changing, not repeating again. All right. Next is we have to do trigonometric and other functions, that graphs, which you all know. I'll not dwell into detail. Basic trigonometric graphs, and tomorrow we will start limits.